Hey everybody, Mr. Judson here. We finally get to start talking about derivatives, all right? And I told you we'd spend all semester talking about them, and here we are, September, October, almost not quite 2 months in, and we haven't even barely said the word. Derivatives. I guess the first thing that I want us to think of is whenever you hear the word derivative, it means slope, all right? Wow, we're going to spend the entire semester, the rest of the semester talking about slope? Yeah, but different ways to find the slope, okay? So first thing we want to know, derivative equals slope. Which a lot of times when we say slope, we also say rate of change. Okay? Every time I say the word derivative, these are the two things we're thinking about, slope or rate of change. And so what exactly does that mean? Because for us, slope is something that applies to a straight line. But yet, we're going to talk about derivatives at different points along a curve. So we've got to kind of change our way of thinking about a slope for a minute here. So let me just draw a quick picture. I've got this graph of some function, f of x. And what I want to do is I want to pick 2 points on this graph, and I want to let those 2 points be fairly close to each other. All right? So I'll go like this. Now, if you look at just the part between the 2 points, that looks pretty close to a straight line. We know it's not. It's a curve. It's not quite straight. Like I can actually see a little bit of a curve in there. But if I took that point and moved it a little bit closer, well then that small part of the curve would look a little bit more like a little piece of a segment. Okay? And so what I want to do is I want to let this point get so close that they're practically touching each other. Matter of fact, I want to take the limit as the distance between those 2 points, the x value, gets pretty close to 0. All right? So here's what I'm going to do. I'm going to say that this right here is some x value, and this red point is going to be at x plus a little bit. Remember how we said delta x represents a very small number? And so what that means is my coordinates for this point are going to be x, comma, f of x. Right? Once I plug x into the function, f of x just means the y value, so whatever I get back. So this is just some xy coordinate. And this point right here has the coordinates x plus a little bit, so x plus delta x, comma, f of x plus delta x. So what I have here is 2 points on this curve. You can kind of see how there would be a line through those 2 points. And what I want to do is I want to let those 2 points get so close together that they might as well be the same point. And then what happens is this red line begins to look like a tangent line. If I kind of draw this curve over here and I say, okay, here's one point and here's the other, and there's my line, this looks like a tangent line. Now, we're not thinking trig right now, right? The word tangent, if you think back to geometry, if you've got a circle and that line comes by and nicks the edge of the circle in one place, that's called a tangent line. So what we're doing is we're trying to make this line nick the edge of the curve in just one spot. There's really two spots, but they're so close together we can't tell the difference. Okay? So what that means now is, and this is where you guys are going to go, oh, that's why we've been doing this. What I'm going to do is I'm going to say that the slope, which is y2 minus y1, so f of x plus delta x minus f of x over x2 minus x1, x plus delta x minus this one. And what I want is I want the limit as delta x gets close to 0. Well, in my denominator I could say x minus x is 0, so those will cancel. And so now what I have is the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And this right here is called our definition of a derivative. And one more thing we want to do is we're going to say f prime of x equals this. When we put that little tick mark there, and it's pronounced f prime of x, that represents a derivative. Okay? It's just a little notation that we add to our function that says whatever f of x is, I want to take the derivative of it. Okay? This right here, you guys, is huge. This is huge for us. Right? We will get a question on the Central Washington test where they ask us to use the definition of a derivative. Everything we do from now on is based on this rule. And we're going to develop some shortcuts on doing derivatives, but it all starts with this rule. Okay? So this is a very important thing. Put a box around this twice. Okay? Maybe 3 times. I don't know. But that's a pretty important idea right there. All right, so how do I use this, and what kind of questions are we going to get asked? Well, we'll get asked questions like this. Find the derivative, I'm going to start abbreviating this, of f of x equals x squared minus 3x. All right? So I want to use this rule right here. What I want to do is I want to say f prime of x, the derivative. By the way, the moment I wrote this down, in our heads we're thinking slope. Right? Let's go back and look at our picture. What I'm finding is the slope of the tangent line. Now, because I could have different tangent lines, let's say I got a tangent line over here, right? There's 2 points that are really close together. Or I could have a tangent line down here. You know, how many different tangent lines are there? There's an infinite number, right? So there's an infinite number of these. When I find the derivative, what I get is an expression that if I plug in any x value, it will tell me what the slope of the tangent line is at that point. Okay? So if I find the slope at this point, I'm going to get a negative answer. If I find the slope down at where the relative minimum is, I'm going to get 0 for an answer. And if I find this slope, I'm going to get something positive. So once we get this function that is a derivative, it allows us to find the slope at several different points. We just got to plug in x values to see what it is. All right? Really important idea. So when I find the derivative of this, what I'm going to get is an expression that I can plug in any number and it will tell me what the slope is at that number. Okay? So let's do this. I've got the limit as delta x approaches 0 of f of x plus delta x. So I'm going to put an x plus delta x in for both of these. So here's my fraction bar. I've got x plus delta x squared minus 3 times x plus delta x minus the original function, which is x squared minus 3x, all over delta x. And now I just got to figure out what that's equal to. See, at this point, we've already done this. We're good the rest of the way down, right? If you want to pause it and try it on your own, go ahead and do that. I'm just going to work through it. Square the first term. Multiply the 2 and double it. Square the last term. Multiply by a -3. Distribute that negative sign. Still doing the limit as delta x approaches 0. And so now that minus that equals 0. -3x plus 3x, that's 0. I can see a delta x in each of those. So I'm going to go ahead and factor it out now. Try and create one less step. So delta x, and I've got 2x plus delta x minus 3 all over delta x. And so that divided by that is 1. I no longer have 0 in the denominator, so I can go ahead and do direct substitution right here. And so if I plug a 0 in, I'm left with 2x minus 3. That's my derivative. Okay? And what it means to me is I can now find the slope of the tangent line to this parabola, right? We know it's a parabola. I can find the slope anywhere along that parabola by just plugging an x value into this. So if I said, what's the slope at 2? Well, that's 4 minus 3, that's 1. What's the slope at -3? Well, I plug that in, I get a -6 minus 3, that's a -9. And if you want to, you can go back and graph that parabola on your calculator, and then just kind of look and see if I did the slope at -3, would it be a steep tangent line on the left side of the parabola? Okay. This is a positive slope, so it's got to be on the right side of the vertex. But it's not a very steep slope, so it's probably pretty close to the vertex. Okay. Where's the vertex at? Remember how we said the vertex is at -b over 2a? We talked about that last year when we did quadratics. So if I did the opposite of this, 3, divided by 2 times 1, that means that my vertex should be at 3/2. Which means, you know, think about the vertex of a parabola. That's right here. The tangent line would be a horizontal line. The slope should be 0. So if I do f prime at 3/2, I've got 2 times 3/2 minus 3. 2's will cancel, so I get 3 minus 3, that's 0. That's what the slope of this tangent line would be. Okay, so at -3, I must be over here somewhere. Something's fairly steep. 2, see that's larger than 3/2. This is 1.5. That's larger, so I'm on this side of the vertex, and I've got a slope of 1. So I'm not real far from the vertex, so 1 is not a very steep slope. Okay, So a derivative helps us find the slope at any point along this curve. All we got to do is plug it in. All right? That right there is what we're spending the rest of the semester talking about. Now, of course, there's a lot of different types of functions, right? We've got trig functions, we've got square roots, we've got fractions. How do you find the derivative of all these different things? That's what's going to take up all the time, right? All right, let's try another one. All right, so I want you guys to try this. I want you to find the derivative of f of x equals a negative 2x squared minus x plus 1. All right? When I first look at this, the first thing that entered my head is, oh, negative sign, upside down parabola. I still want that to happen. I want to know what that looks like before I even do anything with it. Okay? But I don't need to know that to do the derivative. All right, you guys go ahead and try it. So I'm going to write down one thing that's slightly different. I'm going to say that f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. This is the same thing that we wrote down before. It's just instead of using delta x, a lot of calculus books and calculus teachers will use h for the simple reason that it's something easier to write down. Okay? But it means the exact same thing as what we wrote down before. So if you guys decide to use h instead of delta x, that's fine. I'm okay with that. I can go either way. It makes no difference to me. It's kind of like 1/2 versus 0.5. They both mean the same thing. I don't even see anything different there. All right? But this gives us a little bit less to write down. All right, so I'm going to say that f prime of x for this problem is equal to the limit as h approaches 0. If you have delta x, just leave it that way for now. Okay, you can do the next one with h. And I've got this fraction where I'm going to put x plus h in place of these two x's. So I've got a negative 2 times x plus h squared minus x plus h plus 1 minus my original function, minus 2x squared minus x plus 1 all over h. And now I just got to simplify that. So square the first term and multiply it by a negative 2. Multiply the 2 and double it, so that's 2xh times a negative 2. Square the last term, so that'd be h squared times a negative 2. Minus x minus h plus 1. And opposite of everything I see here. Plus 2x squared plus x minus 1. All over h, limit as h approaches 0. So one thing that I told you guys before is all of these things over here that I just took the opposite of, everything that just came from this, it should always cancel out. If it doesn't, that means I made a mistake somewhere. Okay? All right, so let's see. The negative 1, that cancels with the positive 1, positive x with a negative x, 2x squared with a negative 2x squared. And when we look at what's left, so I've got this term, and this term. There's an h in each of those. So I'm going to go ahead and factor one h out. I want that to cancel with the 1 in the denominator. I'm left with a negative 4x minus 2h minus 1. So now that cancels with that. And if I plug a 0 in where I see h, that whole term becomes 0. So I just get a negative 4x minus 1. Oops. So negative 4x minus 1. F prime of x equals that. Sometimes people say, well, where did the limit go? How come you quit writing that down? Well, it's because I could now do direct substitution. I can plug that 0 in here. This is no longer there, so I no longer have h in the denominator. And what I'm doing is I'm just plugging that 0 in right there. There's what I got. So I have now found the derivative. And so now there's some other questions that our book can ask. Okay. They can say, find the slope at x equals, let's just say 2. Find the slope at x equals 2. Well, that's easy. Just plug it in. Negative 8 minus 1. F prime of 2 is going to equal negative 8 minus 1, which is a negative 9. And remember, that's a slope. There's also another question they could ask. And they'll do this. This is a very common question in calculus. Find the equation of the tangent line, which I'm just going to abbreviate this from now on, T-line, okay? Because we get asked that so often that I'm just going to shorten it up a little bit, and whenever you see me write T-line, we're talking about the tangent line, okay? So let's see, equation of a line. Anytime we see that, we need to think to ourselves, and we've been thinking this for 4 years now, all the way back to Algebra 1, maybe longer. To find the equation of a line, I need a slope and a point. And we said derivative always means slope. So I've got my slope. I've got the x-coordinate. I just need the y-coordinate for a point. And how do I get that? I hope when I ask questions like that, you guys are thinking in your head. I hope you're not just staring at me going, well, come on, tell us, Judson. The whole idea is that we think on our own a little bit, right? So a lot of times when I pause with these videos, I'm giving you guys that opportunity to, in your head, go, oh yeah, here's what I do, okay? So how do I find the y value? I got to plug it back into the original function, right? So I'm just going to say f of 2. So let's remind ourselves of the original function. Negative 2x squared minus x plus 1. So let me just write that over here. F of x equals a negative 2x squared minus x plus 1. So f of 2 is going to be 4 times a negative 2. That's a negative 8. Minus 2 plus 1. That's going to be a negative 9. Okay, that's pretty weird. You don't always get the same slope as you do y value. Okay, that's just a coincidence. So I don't want you guys to think that that's a normal thing that happens. Okay. So what I have is the point 2 comma 9, negative 9. And our slope is negative 9. So now I just have to write the equation of that line. So y minus the y value equals the slope times x minus the x value. Alright, so now if I distribute this, I've got y plus 9 equals a negative 9x. Multiply these, you get a positive 18. Move that 9 over and subtract it. I get y equals a negative 9x plus 9. There's my tangent line. Okay, so now what I want to do is I just want to double check my work and see if everything looks right. So I'm going to graph the original equation and the tangent line. And what I want to see is that this tangent line comes by and nicks this curve at x equals 2. All right? So let's grab my calculator. All right, so I got everything cleared off. I'll go ahead and type in the original function first. So I've got a negative 2x squared minus x plus 1. There's that. And now my equation of the tangent line, I've got a negative 9x plus 9. And so now I want to graph those two. I'll just start with zoom option 4. And so there's my parabola. There's my tangent line. I'm going to change the window a little bit so I can kind of see a better picture of what I want to focus on. So I'm going to say, you know, on the x-axis, we really don't need to go that far. We can go from negative 3 to 3. And for my y values, I do need to see a little bit lower than this. So let's maybe go from negative 15 up to 5. And so then I want to graph that again. So there's my parabola. Here's the tangent line. It looks like it's intersecting right about here at x equals 2. There's 1, there's 2. It does look like it comes by and nicks the edge of the parabola and then starts to separate again. So I could even do one more thing. I could say, let's find the point of intersection. Now, remember, we said let these 2 points get so close that there's no distance between them. That's our definition of a derivative. But if I try to find the point of intersection, because we took the limit as x approaches 0, that means technically there's no distance between those 2 points. And so I can't find 2, it's only going to find 1. There's only one point of intersection. All right? So I'm going to go up to my F5 menu, option 5, point of intersection. First curve, second curve, give it a boundary. I think it's somewhere between 1 and 2.4. Right? I already know it's at 2. So I'll go 1 for the left boundary, 2.4 for the other boundary. It's going to work here for a second, and there it is. 1.9999999999995 at negative 8.99999999996. And so, yeah, the calculator worked for a while. It thinks it got pretty close. It isn't quite there yet. It didn't really take the limit as x gets all the way to 0. It just got really close. But for all practical purposes, that is 2 comma negative 9, which is where we said that point of intersection should be. All right. So polynomial functions really aren't too bad. You know, what if we had something different? What if I had something like a fraction? Let's try this. I want you to find the derivative of f of x equals 1 over x squared. Well, we're going to use our definition of a derivative. And I'm going to say that what I want is I'm going to say f prime of x equals the limit as h approaches 0. I want f of x plus h. I want to put an x plus h right there. So 1 over x plus h squared. Minus the original function all over h. You guys see if you can finish that up. Okay? So before you get too far in multiplying this thing out, remember what I kept on saying last year. Anytime you have a complex fraction, right? Fractions within the fraction. What I really want to do is I want to multiply this whole thing by the least common denominator. And our least common denominator is always whatever you see in the first one, x plus h squared, and then whatever you see in the next one if it's not already listed there. I got to think of these as factors. So I know if I multiply this out, I would see an x squared, but it's something that's being added or subtracted. It's not something that's being multiplied. So times x squared. You know, think back to when you first learned how to add or subtract fractions. If you can't find a common denominator, just multiply the two. That's kind of what I'm doing right here. So I want to multiply this by x plus h squared times x squared. I'll do the same thing over here, x plus h squared times x squared. And I'll do the same thing down here, x plus h squared times x squared. All right, so that cancels with that. This cancels with this. And so what I end up with is x squared. So I'm going to write this in the numerator. X squared minus everything that this becomes. All right, so I square the first term and subtract it. Multiply the 2 and double it. So that's 2xh and subtract it. And then you square the last term and subtract it. All over, I'm going to call this hx squared times x plus h squared. Limit as h approaches 0. So I can see that that minus that is 0. All right, so I can see that if I factor an h out of each of those, I get h times a negative 2x minus h. In the denominator, I still have hx squared times x plus h squared. Limit as h approaches 0. If I plug that in now, I'm still going to get 0 in the denominator. But the moment I cancel those h's, I'm no longer going to get 0 in the denominator. So now I can do my direct substitution. So I'm going to put a 0 in here for h. So what I'm left with is a negative 2x in the numerator. In the denominator, I'm going to put a 0 here, so I get x squared times x squared. That's x to the 4th. And so what I get is a negative, this x will cancel with one of those. I get a negative 2 over x cubed. There's my derivative. And so again, we could now ask additional questions like what's the slope at x equals whatever. We'll plug a number into this and get the slope. Or what's the equation of a tangent line if x equals some number? Well, we'd plug it in and get the slope. We'd plug that number back into the original equation to get a point, and then we just got to write the equation of our tangent line. All right, so one more thing that I want us to write down, and that is this. The notation for a derivative. It would be really nice if there was just one way to do it and we always wrote it the same way, but that is not the case. There's actually several ways. So we've already mentioned this, f prime of x. That means a derivative. And if f of x is the same as y, then it would make sense that we could also do this. So f prime of x or y prime, both of those mean the derivative. Okay? This is not as obvious, but dy over dx. It's very common, right? If you think about it, when you find a slope, you're subtracting your y values on top, your x values on the bottom. It means the difference between the y's divided by the difference between the x's. Difference between the y's divided by the difference between the x's. So dy over dx, very common. Okay? Sometimes you would see things written like this. d dx of f of x, or d dx of y, or d dx of a negative x, 2x cubed minus x plus 1. You can actually put an expression in there. This d over dx means the derivative of this with respect to x. When we say with respect to x, that just means that's the variable that we're using. So you guys might remember we have an equation that looks like this. s of t equals a negative 16 t squared plus the initial velocity times t plus the initial height. Some physics, right? This is of an object flying through the air. That negative 16 has to do with gravity pulling it back. Or maybe we've got a negative 9.8? I can't remember what that number is. But we could say ds over dt, which means I want the derivative of this function s with respect to t. Okay? So a lot of times we see it written this way, but with different variables. We just have to realize that all of these mean the same thing. It means find the derivative. Okay? They just have some different ways to write this. I don't know why, but they do. Right? These are the four most common things that I've seen. Off the top of my head, I can't remember if there's like another way they could write it, but if we ever run across it, we'll just mention it then. Okay? They all mean the same thing. All right, let me get you guys a homework assignment. I know it's Monday. I know we just took our test. If you need to put this off till Tuesday, I get it. I understand. But assignment number 7, page 107, we're going to do 5, 11, 13, 25, 27, and 29. One thing that happens here is a typical calculus book punishes students. We do a lot of these. We get really tired of this definition of a derivative, and it's so long. And then all of a sudden we go, hey, guess what? There's a shortcut. We're going to get to the shortcut pretty quick. I told you guys I'm going to try and find some ways to buy some extra time, and we're going to skip the punishing you guys with this long form of a derivative and get right to the shortcut tomorrow. Okay, it's going to allow me to skip a couple sections in the book. So that'll be a good thing. And really, in the end, we want to know how to do the shortcut. That's how we do almost every single problem. You will only have to do this definition of a derivative once for me, once for Central Washington, and at most once on the AP test. Okay? It's all about shortcuts. So we'll move right on past that. Okay? All right, there it is. You guys take care, stay safe. I will see you later. Bye.